Recording. Okay, good afternoon, everybody. Buenas tardes. Now let's proceed to talk about concepts that you guys want to review about chapter 9. Concepts for chapter 9. In chapter 9 is when we had the whole concept of solutions. Any concepts for chapter 9? Okay, so we have dilutions, we have weak versus strong electrolytes. Solubility rules. Molarity. Calculations. Other topics from chapter 9. Then let's get started with these 4, okay? Now, let's tackle the calculations first. Let's do molarity calculations and dilutions first. So when it comes to molarity, okay, remember that is given by the amount of solute in moles. And we are going to divide that by the liters of the solution. So in terms of definition, molarity, which is given by the capital M, which means molar or molar, is always given as moles of solute. And then we have liters of the solution. Okay, so whenever we are dealing with molarity, there's a few things that we can do. Okay, the first calculation that you guys need to be familiar with is just calculate molarity given moles of solute and liters of the solution, or given grams of solute and liters of the solution. Okay, those are the 2 calculations that we have in that front. Now, as we have done, let's actually do some practice problems. Chapter 9. Page. No, there's dilution, molarity. Let me see, maybe they fit here. In problem number 6, as you can see here, we're calculating molarity, and it's just stating that you have 5.00 moles of glucose, and you're going to dissolve that in 15.00 liters of water, okay? So the equation is going to be molarity equal moles per liter. So on the top, we do 5.00 moles of glucose, and we're going to divide that by 15.00 liters. Okay? So we added enough water. Oh, there you go. We do 5.00 divided by 15.00. How many sig figs do we need? Great job. We need 3. So for this one, this is going to be 0.333 molar. So a problem like problem 6 is more straightforward. The problem already stated what is the moles of solute and also what is the liters of the solution that we have. Now, on the top problem, instead of having moles, now we have grams. And when we're giving grams, as we discussed in the first part of today's review, if you're giving grams of solute, the first step is going to be convert that to moles of solute. Okay. Yes, if the volume of your solution is in milliliters, then you need to change it to liters, because molarity is always divided by liters. But I think that I was careful with that in the exam, because you guys have enough calculations to do so. I don't think, I think I was very careful in the exam that your volumes are in liters for your molarity questions. Maybe in the chapter quiz, they could have been milliliters, just to see who's paying attention to the units. And it's mainly because you guys have more time on the chapter quizzes. But I think in the exam, I was careful to make sure that you guys don't have to be struggling like, oh, I still have to change milliliters to liters. There you go. So there was a question on quiz 9. Yeah, in the chapter quizzes, I give you guys, since it is open and you guys usually have a week to complete them. In the chapter quizzes, since you guys have more time technically to complete them, unless you do them the same day that they're due, my expectation is that students are going to be a little bit more careful. In exam settings, because you guys are timed, I have to make sure that this exam is timed appropriately, because I cannot have an exam that it takes the average students 2.5 hours. At least I'm not that type of professor. I do my exams such that the average student should take 1 hour 45 to 2 hours, and everybody should be getting 30 minutes when they finish the exam to review their answers. So be mindful that in this exam, every 10 questions, if you pace yourself right, every section should be taking you 30 minutes or less. That's how you should be pacing yourself. The first 10 questions, let me finish them in about 30 minutes. If you are exceeding 30 minutes, please move on to the next section, because there are some questions in the exam, and that happens in any exam, at least in my course, that are just point grabbers, are, you know, straightforward questions that you don't want to miss those points. So make sure that when you're pacing yourself, this is, again, one of those strategies that I suggest to students, that, you know, give yourself 30 minutes in a section. If it takes you longer than that, please move on to the next one, just because you don't want to miss the easy points. So going back to this one. In this question, we are starting with 2.60 grams of potassium hydroxide. And then we're going to be creating a solution that is going to have a 3.00 liters. Yes, every 10 questions is a chapter, just like in exam 1. I don't know if I mentioned it in class, but then sometimes students don't realize that. So the exams are organized. For those of you that paid attention to that or captured that during exam 1. In exam 1, the first 15 questions was chapter 2. The next 15 questions was chapter 3. The next 15 questions was chapter 4. In this exam, the first 10 questions is chapter 6. The next 10 questions are chapter 7. The next 10 is chapter 9. The next 10 is chapter 10. Now understand that there's some concepts that blend just because you see them throughout, right? So for example, attractive forces, we talked about them in chapter 9, but we started talking about them in chapter 7. So if there's an application question, understand that there's a flow, and then there's some overlaps conceptually, because that's just how the class is built. So when it comes to this question, we're going to write 2.60 grams. The chemical formula of potassium hydroxide is KOH. So what is our conversion factor? If we're going from grams to moles, we're going to from grams of a compound to moles of a compound. Excellent. Molar mass. Great job. We're going to divide by the molar mass. See, you guys got this. I'm telling you, this exam, you're going to take it and be like, okay, it wasn't that bad. So for this molar mass, we're going to take 1 potassium, and potassium is 39.0983 plus oxygen, which is 15.9994 plus 1.00794. So the mass here is going to be 56.10564 grams of KOH, 1 mole of KOH. So when we take 2.60 divided by the 56.10564, we get that the moles are 0.4634, and I'm going to put the 3 dotted lines just because of the calculator display. Then I'm going to divide that value, okay, by the liters of water. How many sig figs in my concentration? We're not looking at decimal places here. We're doing multiplication division. 3 sig figs. So overall is 0.154. Okay. Questions on calculations of molarity. Let me see. If we go, let me just similarly follow mod. Let me open my Canvas. Assignments, chapter 9. Preview. So this is chapter 9 chapter quiz. See, like chapter 19, question 19 in the chapter quiz. You're given moles, you're given liters of solution. In question 20, you can see how the volume is in milliliters? Make sure that your volume, you convert that to liters. So in here, you have to do one more step when you go through here. This is for defining the grams of the solute, which is a different question. Go back. We already talked about the milliliters of water added. This is a dilution question. So question 13 will be like if you're trying to find the grams of solute. We haven't done that calculation yet. Are there questions on calculations like number 13? Go ahead with your question, Gia. Or is it that you're saying one more for the examples?
I did have a question on 13, but I don't remember where I put my notes. I will get back to you on that.
Okay, so let me just go over the logistics of question 13 then.
Okay, that'd be perfect. Thank you.
Let me go back. Let me get another example of molarity. Are we good with molarity? Or Gina, do you want to do one more of the molarity calculations?
Yes, please. I get it, but sometimes I just feel like one more practice would help.
Okay. Let's see. Chapter 9. Let me share my screen. So here we have another example. We have grams of solute, and then it was a milliliter, so I changed it to liters, the volume of water for the solution. So I'm going to give you guys 2 minutes and I'll go over the answer. We'll go through it now. So we start with 6.12 grams of KCl. The first thing we're going to do is change that KCl into moles. So KCl is 39.0983 plus 35.453. That gave me 74.5513 grams of KCl. So the moles, 6.12 divided by 74.5513 is 0.08209 yada 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 moles of KCl, and I divide this by 0.500 liters. I need to round it to 3/6. Divide it by 0.500. There you go. You got it. Yep, you're correct, Francisco. And L got it, Gina got it, Gia got it. There you go. You guys got this. Great job. Excellent. So the other calculation that you guys need to like be aware of when it comes to molarity is if you're trying to calculate grams of solute needed for a solution, okay? So we need to rearrange our molarity equation in order to do this. So we already started saying that molarity equals moles per liter, okay? And then we have to rearrange this squiggly curvy line is my shorthand for rearranging. So for doing this, what we're going to do is that we are going to solve the equation for moles. When we rearrange this equation, all we're doing is multiplying both sides by the liters. So we're going to say molarity times liters will give me the moles of solute. Once I have the moles of solute, if I want grams of the solute, I change moles to grams. Okay, so this is the first equation you're going to use. And then the second equation that you're going to use is taking the moles and changing them to grams. Let me find an example problem for you guys. Calculate molarity, calculate molarity. Here we go. As you can see in this problem, is asking you to calculate the grams of sodium hydroxide that you need in order to make specifically a solution that is 5.00 liters at a concentration of 2.20 molar, okay? So as I said, two things that we need to do. The first thing that we are going to do in terms of the work is that we're going to say, the amount of moles I need of my solute is going to be where I take the molarity, 2.20 molar, and I multiply it by the liters, which is 5.00 liters. Because remember that molarity is the same thing as saying moles per liter, then my unit is going to be moles, okay? So don't be confused in terms of the unit. When you multiply molarity times the liters, moles is your result. So we're going to do 5.00 times 2.20. And you see, when you do that, the calculator display shows you the value of 11. So I'm just going to write 11. And then in the second step, so this was the first thing. In the second step, we're going to say, okay, 11 moles in this case, sodium hydroxide, NaOH, we need to change that into grams. So by now, we should all know, what are we doing in order to change moles to grams? Let's put it in the chat. We're not dividing by the molar mass. The molar mass is on top, right? 1 mole NaOH, because you want to cancel the units diagonally. On top, you put grams of LH. Remember that in dimensional analysis, the reason why I teach dimensional analysis is because you can see the cancellation of the units. You always, whenever you put your conversion factor, you guys, as a fraction, the bottom of your fraction is going to be the unit that you're trying to cancel. The unit that goes on top is where you're transitioning to. So moles of NaOH cancel with moles of NaOH. That's why the grams are on top. So for NaOH, we have 15.9994 plus 1.00794 plus sodium, which is 22.989769. So we find that this is 39. 39.997109. And we multiply that times 11. And we round it to 366, okay? Great job, you guys, exactly. 440, but we need to put the decimal place, because writing that decimal place is what's going to make the zero significant. Should we do one more practice problems? Great. Understand, you guys, for the chapter quiz, you need to change, if your volume is given in milliliters, change it to liters. But for the exam, I was careful not to put milliliters as volume, just because by the time you guys reach chapter 9, you've done a lot of calculations. So I think I was very careful, and I apologize if there's a question that you have to change milliliters to liters, but I don't think I did. So for this problem, which is similar to what you have in the chapter quiz, this value must be changed to liters first. So this is 0.0340 liters. Because remember that the units for molarity is liters. So for the chapter quiz, make sure that you change your milliliters to liters when you're doing this calculation, okay? When you're calculating the grams of solute. So now that you guys have the volume changed to liters, I'm going to give you guys 2 minutes to complete this problem. Love it. You guys are doing these fast. Well, 34.0 milliliters or 0.0340 liters is the same number as sig figs. It's 3. So we need to round to 3 sig figs. So let me do this. Let me check 9 times 0.0340. I got 0.306 moles. And then I'm going to multiply that times the result of taking, what is this? HCl, 1.00794 plus 35.453. There you go. I got the same result. So it should be 11.2. Yes, it should be 11.2. Ooh. Okay, let me write the work and let's re-enter it. So we're going to do first the moles, which is 9.00 molar times 0.0340 liters. That is 0.306 moles. Did you get the numbers up to this point, Gina? Okay, and then you're going to say 0.306 moles. And then 1 mole, we have HCl. And then the molar mass of HCl is going to be 35.453 plus 1.00794. So this is 36.46094 grams of HCl. 1.306. Okay, be careful when you guys are entering things in the calculator. Like I understand that, especially if you're working with a graphing calculator, some students just like to enter the whole thing. But if you don't use the correct parentheses, then all of a sudden it can affect your result. Okay, what's the molar mass? Any other questions on molarity? Make sure that you write it, like even if you're at home doing these exams, have scratch paper and you can trace your work and see that you wrote it down. After I make the exams, like I actually take the exam and I sit down with my periodic table calculator and scratch paper and I go through it to make sure that, you know, that I read through the question, that I check that the numbers are there, that the answer is there, that I selected the correct answer. Great. So let's go over dilutions. In dilutions, oh wait, this is organic chemistry. For dilutions, remember that is M1 times V1 equals M2 V2, okay? The volume of what you're diluting, as long as they're the same, meaning they're both milliliters, they're both liters, that's okay. So let's go through these two. Oh, I didn't copy it. Ay, carrillo. Copy. So again, whenever we're doing dilutions, we're doing M1V1. M1 times V1 equals M2 times V2. And this is the concentrated solution. Concentrated. And this is your diluted solution. Okay? So when it comes to this, you can see that the first one says 140 milliliters of bicarbonate solution. Let me put the negative sign here. Is diluted to 500. And that final concentration is 3.25. And then it's asking what is the initial molarity. So what are we solving? Which term are we solving for? Based on reading the question, what term are we solving for? Excellent, the concentrated. So what is it? We call it M, what? Is it 1 or 2? What are we solving for? Great job, we're solving for M1. So if we isolate the term FM1, that means that M1 equals M2 times V2, everything over V1. And we just put in the numbers, you guys. 3.25 molar times my final, which is 500 milliliters, divided by 140. You don't need to change to liters, because you can see here, milliliters cancel with each other. 3.25 por 500 dividido entre 140. And then everything has 3 sixes. So the concentrated solution was 11.6 molar. Excellent. Yes. Let's look at the second one. This in dilution equations is more about reading the question and understanding what is it that I need to find. Go ahead, Elle. Uh-huh. You don't need to change it to liters unless the answers that you see are in liters. Like if you have a multiple choice question, but then when you calculate it out, you end up in milliliters, but then the answers are given in liters, that's the only time that you need to do that. Let me see, in chapter 9, chapter quiz, is there something like that? No, this is molarity. We already went through that. No, there's not a question like that. You, unless you're prompted to it. Oh, give me one moment, you guys. I'm back. I'm sorry, you guys. It's just that Fridays I usually don't teach, so I get phone calls and I get called for meetings, all that kind of stuff. But I'm back. What was I thinking? Oh, Francisco left. No problem. What was I thinking? Oh, there was a question here in the chat before. Worksheet chapter 9, section 3. Worksheet chapter 9. Section 3. Oh, for the dilutions section. No, again, when it comes to this, unless you're prompted to do milliliters, just look at the units that you have in the multiple choice. But again, at this time during the exam, I'm already picturing that my poor students are a little bit cross-eyed just because they have been using the calculator a little bit too much. So I don't test you guys at this point in the exam on unit conversions. I do it in the homework, just because you guys have more time. Okay, so we did. Do I need to go over 17? Let me share my screen again. So number 17 says, find the molarity of a 6.00 sodium carbonate solution with a volume of 565 that is diluted to a volume of 1,560. If you guys want, we can go over solubility rules. We can move on to solubility rules. Okay. When it comes to weak and strong electrolytes, what's the specific question?
I guess just how to like identify it. Do you just go off of the list from chapter 10 for weak bases and weak acids, or no?
No, yeah, you're correct. So when it comes to strong electrolytes, because they break into ions, okay, in your solvent is going to be strong acids and strong bases. So remember, there's 6 strong acids, and then there are the bases that are group 1A, group 2A, and hydroxide. So those are going to be your strong electrolytes. Your weak electrolytes is going to be anything else that is not in that list. The non-electrolytes, we typically don't talk about them often in class because we do not see them until we do organic chemistry. But understand that those are not going to break into ions at all. So it's mostly going to be covalent compounds that do not break into ions at all. So they don't have, some of them can have hydrogen, but they don't have the ability to break into ions. That's what it is. Yes, Elle, you're correct. The strong ones is all ions. They're able to form cation and anion. And then the weak ones, some ions, but it's mostly molecules. And then non-electrolytes is going to be no ions at all. Let's go through solubility rules. I think that what was mentioned on the chat, that it was just a review of what the solubility rules are. So solubility rules are going to be important in two types of questions, okay? The type of questions are, first, if you are trying to find, if you have a double replacement reaction is what I'm trying to say. And then you're trying to figure out, do you form a precipitate, okay? And which one is the one that is solid and which one is the one that is aqueous. The other instance in which solubility rules are used is if you have to determine the solvent for making a solution. For ionic compounds, you will be using solubility rules to determine if the ionic compound is soluble in water. So if it is, then it can make a solution with water. If it's not soluble in water, then it will make a solution with a non-polar solvent. And those are the two instances in which we use solubility rules. So when it comes to the rules themselves, this specifically is slide 6 in chapter 9. So that's where you have your solubility rules. So to review the solubility rules, so should we review them? Let me know. Like I can walk through this slide again.
No, Professor, I think it's more like when we have questions that come up, we just refer back to the solubility rule, right? That's like the rule of thumb. When we have the questions come up regarding solubility, we just come back to this table.
Yes, but but like I just mentioned, it's those two type of questions. So remember that this is going to be your strategy for questions that, number one, you have a double replacement reaction like we did in class. You have a double replacement reaction. You do the double replacement reaction, and then you determine if your product is solid or aqueous. And then the other time that you use your solubility rules is if you have a particular molecule, it is an ionic compound, and you need to decide, is it soluble in water or is it not soluble in water? If it is soluble in water, then water is the solvent for making a solution. If it's not soluble in water, then a non-polar solvent is what's going to make it a solution. Again, that is for ionic compounds. For molecular compounds in this question, as you can see here, we need to draw the Lewis structure, determine the overall polarity, and then select the solvent that matches the polarity. So those are the two instances. Any questions on chapter 9, or out of the two instances where you need the information, is there something that you guys would like to practice?
No, I think I get it. Like I said, it's just about looking at the tables a little bit longer and kind of understanding what is being asked of you in the questions. Maybe like an example. I don't know. What do you guys think?
So in the chat, Elle mentioned number 13. So we have lead acetate, okay? So for lead acetate, are we doing Lewis structure or are we using solubility rules? Let's determine that. For lead acetate, are we doing the Lewis structure or are we using solubility rules? Excellent, solubility rules because we have an ionic compound, okay? So we go here. Then we have to say, sorry, I just kept on getting messages for meetings. Anyways, going back to this. So we have lead 1 acetate, right? So when we look at the rules, acetate, okay, is on rule number 2. You guys see that? The C2H3O minus, that's acetate. So see what it says in the blue notes that I did. Any cation paired with acetate or nitrate, in this case, we're doing acetate, will be soluble in water, and that is always. So if lead 1 acetate needs a solvent, since it's soluble in water, we will be able to use a polar solvent like water to make a solution. There you go, exactly. Let's look at sodium nitrate, number 15. Let's go to solubility rules. Sodium nitrate, is it soluble in water? Yes or no? Where is nitrate? Which rule? Great, I like those yeses. Rule number 2 tells you, great job, you guys. Rule number 2 tells you that specifically the nitrates are actually soluble in water. So a polar solvent like water will make a solution, okay? Any other concepts of chapter 9? If not, we can move on to chapter 10. Okay. Here. So the last chapter. Oh, great question, Gia. What precipitates in a double replacement reaction is whatever is not soluble in water. So if you find that something is insoluble in water, then that's what forms the precipitate. That's what forms the solid.
Say it again. Whatever is non-soluble in water forms a precipitate.
Yep. That's what crashes. If you're not soluble in water, in an aqueous solution, you will form a precipitate. Exactly. We're talking about ionic compounds in a double replacement reaction. And the reason why they form a precipitate is because they are in an aqueous system, right? So if we because look at the image here. You have potassium iodide that is aqueous. That's why it's a clear colorless liquid. you have lead-2 nitrate, which is whatever is surrounding the yellow. After the exchange of ions, then that lead-2 iodide, since it is insoluble in this system where water is our solvent, because remember that that's what an aqueous solution is. Water is our solvent. All these ionic solids are soluble in water. That's what makes you aqueous. So in this water environment, once those ions exchange and that lead-2 meets that iodine, it precipitates. And that's where that you see that yellow compound. They're fun reactions. The copper ones are super pretty precipitates. They're green or cobalt blue. Sometimes they're turquoise. Those reactions are really nice in terms of the precipitate color that you get. So let's go back to chapter 10. What concepts of chapter 10 would you guys like to go over? No problem. Naming. Yeah, acids or bases? Any other topics from chapter 10? Question 9 in where? Oh, chapter 10 quiz. Let me just open that. Chapter 10. Let me see, question 9. What's it say? Okay, so question 9 in the chapter 10 chapter quiz. That is a pH calculation. So we can go over that. Okay, anything else? Okay, so let's get started with naming. Out of the two namings, the bases are the easier, okay? Because naming bases, if your base starts with group 1A or group 2A metals in it, you're going to use the name of the element. They're going to be paired with hydroxide. So you will use the word hydroxide. So let's say, periodic table, KOH, BaOH2, MgOH. Okay. Or even if you have things for group 3A, right? Do we just use the name of the element? So what would be the name of KOH? Excellent, potassium hydroxide. And what about BaOH2? Great, barium hydroxide. What about MgOH2? Great, that's magnesium hydroxide. Give me a moment. Okay, so that's pretty much how we handle the bases. Other than that, we have two weak bases, phosphine and ammonia. And that's pretty much it. When it comes to naming the acids, then that is, I gave you guys, let me go back to the presentation. What you guys already have the list of the binary acids, and remember they start with hydro, hydrosulfuric acid, hydroselenic acid, hydrofluoric acid, hydrochloric acid, hydrobromic, hydroiodic. Because in binary acid, you start with the word hydro, you use the stem of the name of the nonmetal that is there, and then you end with ic acid. Okay. The oxy acids are the ones that, remember, they're going to start with hydrogen, followed by a polyatomic. And then if your polyatomic ends in ATE, then the name of the acid will end in ic acid. But if it ends in ITE, then the ending is going to be instead ose acid. The only ones that you guys have to be conscious about is the sulfates and the phosphates, just because the endings is not the only thing you change, because phosphate turns into phosphoric or phosphorus. And then the sulfates turn into sulfuric or sulfurous acid. Any other questions in naming? Yeah, only those two. Everybody else is going to follow these rules. And then, of course, the exception that I explained in class, that the cyanic acid is the only one that has hydro. So HCN is the only one in the crew of the polyatomics that has the word hydro.
Wait, which one has the hydro?
Cyanic, you see it in the corner in the notes, HCN. That's the only acid coming out of a polyatomic that has the word hydro in its name. Other questions in naming?
So for phosphorus, there's only two ways to change that. Phosphoric and what's the other one?
Phosphorus. So if
Phosphorus.
you have H3PO4, this is phosphoric acid. H3PO3, that's phosphorus acid. And then the other one is the H2SO4 versus H2SO3. This is sulfuric acid, and this is sulfurous acid. Because the rule really doesn't follow through. Like if you think, oh, sulfate, I remove the 8 and I put ic acid. It's not sulfic acid, it's actually sulfuric. That's because the stem for phosphorus and sulfur is different from the other nonmetals. It's just one of those things that that comes with practice and getting familiarized. Any other questions with nomenclature of acids and bases? What questions do you guys have in terms of pH calculations?
How did it determine something is more like, so for example, in question 10, was it question 10 that I said? I got that one wrong. And I just plugged in the numbers that they add, like, you know how that gives you hydrogen 1.1 times 10 to the 4th.
Let me see.
It said what would produce pH that is basic. And then your hint was determine the pH value. No, determine the pH based on the values given. So when I did it, I got like 7 times 10 to the 0. And I wasn't sure how to compare the numbers that I had to what is acidic, neutral, or basic.
Okay, so let me share my screen. So this question in the chapter quiz, question 9?
Yes.
Okay.
Yes.
So here in A, B, and C, you can calculate what is the pH directly because you have concentration of protons, meaning hydrogen ion. So the pH of the first one is 4. The pH of the next one is 7. The pH of the next one is 10. For you guys that are like, how do you know how to do this calculation? I'm not even using my calculator. Because I explained in class that if your coefficient is 1.0 or 1.00, it has to be 1.0 or 1.00. Your exponent as a positive value is your pH. So the pH of the first one is 4, the pH of the second one is 7, the pH of the last one is 10. Letter D is hydroxide. So for getting the pH on letter D, you need to do 1 times 10 to the negative 14 divided by that number, which is going to be 1 times 10 to the negative 7 So D and B are the same answer. So then, as you can see, if you're comparing pH of 4, pH of 7, pH of 10, and pH of 7 again, which one is more basic? Which is what the question is asking.
Well, if it's more basic, then it would be the one. Basic is is greater than 7. So that would be 10.
There you go.
Just C. Oh, and then, sorry, just a question for the 1.0. So again, if you said if the 1.0, what do you call that? If the
Coefficient.
If the coefficient is 1.0 or 1.00, then you get your pH level off of
The number in the exponent. See how we have that number in the exponent? -4, -7, -10, -7.
yes.
So for the first three, because they are representing concentration of proton, then technically, if you take those numbers and you put them in the calculator, you will see that what you get is the value of 4. So you can try, you can plug it in. Do negative log of 1.0 times 10 to the -4. You will see that your pH is 4. Same for, B and C. You will see that the result, it will tell you 7. For C, the result will be 10. In D, the only reason why we needed to do one more step is because hydroxide is what's given to us. That's just one of those shortcuts that you learned from experience or from the notes in the class, that whenever you have a coefficient, so the number, the values before the times 10, when that is 1.0 or 1.00, don't even plug it into the calculator. Look at the exponent, turn it into a positive number. That's your pH. Other questions on pH calculations? No problem. Let me share my iPad. So when you guys are doing pH calculations for the exam, okay, understand that there are 4 equations that you need. That is your toolbox, these 4 equations. First one, pH equals the negative log of the concentration of H plus. Remember that H plus is the same thing as talking about H3O plus, which is hydronium. Second equation, what if I'm interested in the concentration of proton, or for that matter, of hydronium? I'm going to do 10 to the negative pH. Next equation, if I'm given hydroxide concentration, I can actually calculate the concentration of proton by saying 1.0 times 10 to the negative 14 molar divided by the concentration of OH gives me my H plus, which is what I did in the problem. Letter D is the concentration of OH. So I did 1.0 times 10 to the negative 14 divided by the concentration Don't apologize, it's fine. It's better to have questions than not to have questions. So equation C is the first thing I used in the letter D in the chapter quiz because it was given to me in terms of hydroxide. And I need it in terms of H plus because look, equation A needs H plus, not OH minus. And then the last one is that, let's say that you're interested in the concentration of OH minus, then you're going to tell yourself 1.0 times 10 to the negative 14 divided by the concentration of H plus is what gives you that OH minus concentration. So these are the four, this is your toolbox for doing pH calculations. Then you just have to make sure that you read what the question is asking. So let me just bring a couple of questions so we can see what equations from our toolbox we need. Let's try to practice by filling in a table. Okay, so when we look at this table, okay, in the first amount, what we have is 1.77 times 10 to the negative 4. So that value, we can now do the trick that I showed you guys, because again, the coefficient is 1.77, not 1.00. So if we are given H plus, okay, which equation do we utilize to calculate concentration of OH, which is the next column in my table? A, B, C, or D? Think about it. So we're here. We're here and we're moving to find out this value. So we are given H plus and we're trying to do OH minus. There you go, letter D. So if I take this number and I say 1 times 10 to the negative 14, and I divide it by 1.77 times 10 to the negative 4. 5.65 times 10 to the negative 11, and then molar is the unit. Okay, I just divided 1.0 times 10 to the negative 14 by that value. Now, if I'm given this, how do I find pH? Which equation do I need? A, B, C, or D? Great job, exactly. We need equation A. So we're going to do negative log of 1.77 times 10 to the negative 4. Okay, so we find a pH of 3.75. So is that an acid or base or neutral? Great job. Let's try the second one. I'm given pH. In terms of strategy, it should be easier if I'm given pH that I find H plus concentration. Which equation do I need? If I'm given pH and I need to find H plus concentration. Letter B. Because look, remember that what we're trying to find is going to be on the left of the equation. What we are inputting into our equation is going to be on the right side. So if we do 5.25, it has to be a negative value, 10 to the x. This is 5.62 times 10 to the negative 6 molar. And now that we have H plus, then we can find OH. Which equation? So if you have H plus, you're going to plug it into the right side of the equation. Excellent. We do letter D. So we do 1.0 times 10 to the negative 14 divided by 5.62 times 10 to the negative 6. This is 1.78 times 10 to the negative 9. But at a pH of 5.25, is that an acid, a base, or neutral? Great, this is an acid also. Now, whenever we have something neutral, what is the pH for something neutral? Great, so that means that this is 1.0 times 10 to the negative 7 molar, and this is 1.0 times 10 to the negative 7 molar. That is known. You could use the equations above, but trust me, that is known. Let's do the very last one. I get hydroxide. So if I'm given hydroxide, think of the strategy. What would be the fastest number that you can produce? Would it be pH or would it be H plus? If I have OH and I look at my equations, where is OH? On the right side of the equation. Excellent, letter C. So strategizing this, I will find this value first. I will say 1.0 times 10 to the negative 14 divided by 3.98 times 10 to the negative 4. This is 2.51 times 10 to the negative 11 molar. Now that I have H plus, then I use equation A and I find my pH. Which this pH is going to be, let's say 10.60. Oh, thank you. This is molar. And then when we have a pH at 10.60, is that acidic, basic, or neutral? Great, this is basic. other questions on calculations for pH? This exam has a lot of calculations, but pace yourself. Any other questions? You guys will be fine. Remember, if there's a question that is intimidating, have the mindset. The question is a puppy or a kitten, whatever animal you prefer. You guys got this. Just have your notes ready. Just be ready when you sit down, be present in your exam and breathe. Yes, you just have to breathe. I know that it's nervous, you know, that there's a lot of nervous energy whenever you take an exam, especially if it's timed. But, you know, do your best. You guys can do this.
Thanks, Professor. That was, yeah, we went over a lot today. I think I
Yeah.
feel more confident. Oh, wait, I have a question.
Yes, if your coefficient is 1.0, your exponent as a positive value is your pH. If it's 1.01, please don't. It has to be 1.0 or 1.00. If it's 1.01, 1.02, 1.05, no, it's only 1.0 or 1.00. No problem. Let me just stop this.